Orca 2 significantly surpasses models of similar size and attains performance levels similar or better to those of models 5 to 10 times larger. Small models have never been able to perform as well as their larger counterparts at logic and reasoning. Until now. We have a brand new research paper out of Microsoft Research called Orca 2, and this is the sequel to the Orca paper, which really improved the way that smaller large language models worked. And now what they're claiming is that smaller models can perform just as good as large models, and the results are stunning. So I'm going to break down the research paper, and then I'm going to test it myself using the Orca 2 model. Let's go. This is the Orca 2 research paper. If you remember, I already created a video about Orca 1. I'll drop the link to the video in the description below. This takes all the learnings from Orca 1 and builds on top of it and brings it so much further. Orca 2, teaching small language models how to reason. Now, I read through this entire paper and I've highlighted the most interesting bits. So let's go through it. So as a reminder, Orca 1 learns from rich signals such as explanation traces. And what that basically means and what the premise of the original Orca paper was is if you fine-tune a small model to understand how step-by-step logical reasoning works, then they're going to be really good at logical reasoning. And this allowed it to outperform conventional instruction-tuned models on benchmarks. So that's really important. Rather than it just being instruction-tuned, which is prompt plus response and teaching it, here's the instruction, here's what I want you to do, it's actually teaching it how to reason through different problems. In Orca 2, we continue exploring how improved training signals can enhance smaller LMs' reasoning abilities. Research on training small LMs has often relied on imitation learning to replicate the output of more capable models. We contend that excessive emphasis on imitation may restrict the potential of smaller models. When the original Orca paper came out, a lot of people said it's just mimicking what these better, larger models are doing. It doesn't actually have that core understanding of why it's doing things. And that's the real way to achieve intelligence with large language models. The basic difference is understanding that 2 plus 2 equals 4. So when you have two objects and you have another two objects and you combine them together, you now have 4 objects. Previously, when we focused too much on mimicking the results, what the model actually knew was anytime you see the characters 2 plus 2 equals, you should know the next character in that sequence is 4. So although it got the answer right, it didn't really understand how it arrived there. So if you ever tried to push it beyond those basic examples, that's when you started to see poor performance. And that's what Orca 2 is claiming to have addressed. In Orca 2, we teach the model various reasoning techniques. So these are all things that prompt engineers have figured out over the last few years. Step by step, which is something that I include in all my prompts, basically instruction and then explain your reasoning step by step. And that definitely produces better results. And here is the most important part. Here is the goal of the paper. We aim to help the model learn to determine the most effective solution strategy for each task. So not only are they trying to move away from just mimicking what these large models are doing, they're giving them tools to actually be able to reason through problems. And not only the tools, but to know which tools to use given each problem. Orca 2 significantly surpasses models of similar size and attains performance levels similar or better to those of models 5 to 10 times larger, as assessed on complex tasks that test advanced reasoning abilities in zero-shot settings. So just a reminder, zero-shot means you only give it one chance to get the answer right. You're not nudging it, you're not giving it hints, nothing like that. So here are the overall results, but I don't want to get too deep into this, but what you can see here is that the Orca 2 13B, this dark line right there, is doing better than any of the other open source models, even the 70B models. And here is Wizard LM 70B model, so it beats them all in every single benchmark, except for this GSM AK, which is a math benchmark. So now I want to show you an example of a logic and reasoning problem. I am going to add this to my LLM test rubric because it is so good and is so clear. There is no way to misinterpret what we are asking. So the question is, John and Mark are in a room with a ball, a basket, and a box. John puts the ball in the box and leaves for work. While John is away, Mark puts the ball in the basket and then leaves for school. They both come back back together later in the day, and they do not know what happened in the room after each of them left the room. Where do they think the ball is? So John put the ball in the box and then he left. So as far as he knows, the ball is in the box. Then Mark, while John was away, put the ball in the basket. Then he left. So as far as Mark is concerned, the ball's in the basket. So that's the answer. John thinks the ball's in the box. Mark thinks the ball is in the basket. And this might seem simple, but LLMs struggle with this type of logic and reasoning, as you've seen in many of my LLM test videos. So let's see how it did. First, Orca 2 13b. Let's analyze the situation step by step. So it automatically knew to use step-by-step reasoning, which is a prompting technique to solve this problem. John puts the ball in the box. John leaves for work. Mark comes into the room and puts the ball in the basket. Mark leaves for school. John and Mark both return to the room. At this point, John and Mark have not seen each other's actions. Therefore, they only know what happened while they were in the room. This is all perfectly correct. John only saw the ball in the box before he left for work. Mark only saw the ball in the basket before he left for school. Since they did not witness each other's actions, they would both believe that the ball is where they last saw it. So John thinks it's in the box. Mark thinks it's in the basket. Perfect answer. Got it right. Now let's look at Llama 2 13b. Answer: the ball is still in the box because it was there when John left the room. So that is already incorrect. And that's not even what we're asking. We're not asking where the ball is currently. We're asking where they think the ball is. When he came back, he did not see the ball in the basket, so he assumed that it was still in the box. And then I don't really understand anything here. It kind of goes off on a tangent. I'm not sure if this was just a complete hallucination or this was supposed to be here. I'm just not sure. But he goes on to say, a man walks into a bar and asks for a drink. The bartender says, "I'm sorry, we don't serve alcohol here." What does the man mean by his response? And he even gets that wrong. So moving on, now for Llama 2 Chat 13b, this is a classic lateral thinking puzzle. The solution is that the ball is still in the box. Again, not right, and not even what we're asking. Here's the reasoning. John put the ball in the box. Mark put the ball in the basket. Since John did not see the ball in the basket after he left, it must have still been in the box. Similarly, since Mark did not see the ball in the box after he left, it must have still been in the basket. Therefore, the ball is still in the box. So they're kind of circling around the answer, but still did not get it. And now, ChatGPT 3.5 Turbo. John and Mark will likely think that the ball is in the box. That's wrong. So not even GPT 3.5 Turbo got it right. But if we look again, Orca 2 13b, perfect answer. Now that we understand the types of reasoning problems that Orca 2 is striving to get right, now let's read a little bit about the techniques they use to actually achieve that. First, they talk about how scaling LLMs like these frontier large language models, GPT-4 and PaLM 2, to ever more parameters led to emergent abilities, unseen in smaller models, most notably remarkable ability to reason at zero shot. Then they talk about imitation learning has emerged as the go-to approach to improve small language models. So basically using these larger language models to do the reasoning and then fine-tuning the smaller model on that reasoning. So it's basically just learning from a teacher. If you can think about these large frontier models are the teacher and the smaller fine-tuned models are the student. But the problem is the student won't ever be as good or surpass the teacher. They often fall short of their reasoning and comprehension skills. In this work, we continue to pursue the question of how we can teach smaller language models to reason. And here's where they start to talk about what techniques they're using that are Orca 2 specific. Firstly, we aim to teach smaller models how to use a suite of reasoning techniques, such as step-by-step processing, recall then generate, recall reason generate, extract generate, and direct answer methods. So not only teaching them about the methods, but teaching them which methods to choose. Secondly, we aspire to help these models decide when to use the most effective reasoning strategy for the task at hand, allowing them to perform at their best irrespective of their size. Like Orca 1, we utilize more capable LLMs to demonstrate various reasoning strategies across various tasks. And when they're talking about more capable LLMs, they're talking about frontier models. However, in Orca 2, the reasoning strategies are carefully tailored to the task at hand. And that's something that was missing from Orca 1 that they're improving on with Orca 2. And it made a huge difference. To produce this nuanced data, the more capable LLM is presented with intricate prompts designed to elicit specific strategic behaviors. So basically, they're handcrafting these prompts prompts saying, here's the problem, here's exactly how I want you to solve it, now go solve it. And then the smaller model is exposed only to the task and the resultant behavior without visibility into the original prompts that triggered such behavior. So basically they have the problem and they have the solution, but they're not showing them the part of the prompts that actually instructed the larger model of how to solve it. And that's a really, really important aspect of this technique. And it's called prompt erasure. And it makes Orca 2 a cautious reasoner. That's what they're calling it, cautious reasoner, because it learns not only how to execute specific reasoning steps, but to strategize at a higher level how to approach a particular task. Rather than naively imitating powerful LLMs, we treat them as a reservoir of behaviors from which we carefully select those best suited for the task at hand. It's so interesting. Here they talk about how they're actually evaluating the results. How are they actually going to measure Orca 2 versus Orca 1 and versus other open source models and even GPT 3.5 and GPT 4. In this work, we provide a comprehensive evaluation comparing Orca 2 to several other models. Now I want to pause for a second about evaluation. I'm currently reading a research paper about contamination. And I'm not claiming that there's contamination here, but contamination is certainly an issue. And just a quick summary, contamination means that they're finding the benchmark data in the training sets of the models themselves, which basically means that the models are being trained to answer the benchmark questions perfectly. Whereas if it's anything outside of those benchmark questions, they're not going to perform nearly as well. So they're basically performing much better than they really should be. We use a total of 15 benchmarks covering 100 tasks over 36,000 unique prompts. The benchmarks cover a variety of aspects, including language understanding, common sense reasoning, multi-step reasoning, math problem solving, reading comprehension, summarization, groundedness, truthfulness, and toxic content generation and identification. And we're going to talk about all of those things. Here they say our preliminary results indicate that Orca 2 significantly surpasses models of a similar size, even matching or exceeding those 5 to 10 times larger, especially on tasks that require reasoning. And from my large language model tests, the logic and reasoning tests are always the ones that the models struggle with the most. Now, this next sentence is so critical and actually ties back to Q-star, it ties back to synthetic data. So let's read this one carefully. However, Orca 2 is no exception to the phenomenon that all models are to some extent constrained by their underlying pre-trained model. So I've been saying this lately, but models are only as good as the underlying data that they have. I don't truly believe that they're coming up with new and novel ideas. The counterexample to that is the AlphaGo technique or the self-improvement technique, and this requires synthetic data. We have two different models, slightly varied, and they compete against each other for the best result, and they continue to iterate and learn from those results. And again, that works really well with a very structured game like Go, where knowing whether a solution is good or bad, whether someone won or lost, is easily discovered. Whereas with just natural language, how do you know something is the best or the worst or anywhere in between? More on that soon. So let's talk about instruction tuning. Instruction tuning has emerged as a crucial step in training language models. Instruction tuning involves learning from input-output pairs where the input is natural language task description and the output is a demonstration of the desired behavior. So basically some kind of prompt and then the response from the model. And what we have found is that having a relatively small amount of that fine-tuning instruction data actually improves the performance of raw models really well. Instruction tuning has been shown to improve the model's ability to follow instructions on both seen and unseen tasks, improve the overall quality of the generations, and give models enhanced zero-shot and reasoning capabilities. However, as shown in these papers, it may not result in proportional improvement to small model performance when thoroughly evaluated on knowledge-intensive or reasoning-intensive tasks where correctness is not just judged by style. And that's really important. What fine-tuning really does is makes a model perform really good at style mimicking, but doesn't necessarily give it that underlying knowledge or the intelligence to answer questions that might be outside of the style that they are mimicking. And here it's says that right here. We note that instruction tuning, while very beneficial for teaching the model how to solve a task, does not necessarily teach the model new knowledge. Hence, instruction-tuned models will always be limited by the knowledge learned during pre-training. And again, I'm going to reference back to Q-star. That's maybe what OpenAI solved with Q-star. Then We had explanation tuning, which Orca 1 proved can really enhance the abilities of small language models. One of the known weaknesses of instruction tuning is that a resulting student model can learn to generate stylistically correct but ultimately wrong outputs. In Orca 1, we introduced explanation tuning. Explanation tuning begins with a complication of n handcrafted general-purpose system instructions designed to elicit more careful reasoning. So a couple examples: think step by step, generate detailed answers, and all of this is just really prompting a smaller model to think slowly, which large models and frontier models like GPT-4 do incredibly well. But now we get to the evolution of Orca with Orca 2. The key to explanation tuning is the extraction of answers with detailed explanations from LLMs based on system instructions. However, not every combination of system instruction cross-task is appropriate, and in fact, the response quality can vary significantly based on the strategy described in the system instruction. So what it's basically saying is not every problem can be enhanced by just saying solve it step by step. And all of the techniques suffer from this. You need to find the right tool for the right job. Even powerful models like GPT-4 are susceptible to this variation. So consider figure 3, which shows 4 different answers from GPT-4 obtained with 4 different system instructions given a question of story reordering. The first answer is wrong. The second answer is better. We can see that the model is reasoning with step by step, but important details guiding the decision process are still missing. The third answer is wrong, but the explanation is correct. And then the final answer is only correct and is obtained using the following system instruction. And so this is really the important part. It's not just about how powerful the model is, and it's not just about prompting the model to use any tool for the job. You have to prompt it with the right model. So the final correct answer uses this prompt. And a reminder, the problem that we're trying to solve here is we have a series of sentences that form a story, but they're out of order. And the job is to put them in order. So first, identify the main theme or the topic of the story, then look for any cause and effect relationships between the sentences, find the sentence that could be, rearrange the sentences in the correct order, and then give the final answer. All right, so let's skip down. So we have sentence 1, 2, 3, 4, 5, and these are all part of a story that are completely out of order. So the first answer is wrong. So let's look. First answer says 43152. So sentence 4, Bruce was a police officer who handled traffic accidents. Then 3, one day Bruce was called to an accident scene. Then 1, he was scared until he found out she was okay. So that's where it breaks. So that is not the correct ordering of the story. So I'm not going to go through all of these, but then we have the final one. When we gave it the right prompt with the right tool set, then it got it right. So the main theme of the story is about Bruce, a police officer, handling a traffic accident involving a friend, Tanya. Cause and effect relationships, listed them. Then the sentence that could be the beginning of the story was Bruce is a police officer who handled traffic accidents, and then rearranging it, the final answer is 42351, which is the correct order. So what does all this mean? It means you need to give the right tool for the right job. So we note that GPT-4's response is significantly influenced by the given system instructions. Motivated by these observations, we conclude that the strategy an LLM uses to reason about a task should depend on the task itself. It is important to note that the optimal strategy might vary depending on the task. The optimal strategy for a smaller model may differ from that of a more powerful one. So even if you have the same problem, the fact that we have a smaller, less capable model compared to a larger model means that the actual tool being used might be different. So for instance, while a model like GPT-4 may easily generate a direct answer, a smaller model might lack this capability and require a different approach, such as thinking step by step. Then they use the term cautious reasoning. So let's take a look at what that is. The following illustrates the process of training a cautious reasoning LLM. Start with a collection of diverse tasks. Guided by the performance of Orca, decide which tasks require which solution strategy. So direct answer, step by step, explain then, answer, write task-specific system instructions corresponding to the chosen strategy, then prompt erasing. And this is an important part. At training time, replace the student's system instruction with a generic one vacated of details of how to approach the task. And this prompt erasing technique is attempting to remove just mimicking what it's seeing. It's actually trying to get it to think and reason about what tool might be right for the job. All right, now just a little bit about the data set that they used. So for Orca 2, we created a new data set with 817,000 training instances. Orca 2 has been trained with progressive learning with subsets of data obtained from combining the original FLAN annotations. Orca 1 dataset and the Orca 2 dataset. And here is just a bunch of information about the training and the data. And I'm not going to go into this, but if you want to read it, I'll drop a link to this research paper in the description below. And now let's talk about all the different benchmarks that they're using. And I'm going to quickly go through this, but I find this really interesting. So first, they're using AGI eval, which is standardized tests, including general college admission tests like GRE, GMAT, and SAT, and LSAT. And then they test for discrete reasoning over paragraphs, or DROP, which is a reading comprehension benchmark. They use the CRAS benchmark, which is counterfactual reasoning abilities, race, reading comprehension, derived from English examinations given to Chinese students aged between 12 and 18. Big Bench Hard, 23 hardest tasks of Big Bench with a focus on challenging tasks such as those requiring multi-step reasoning. The GSM 8K, which is a collection of word problems that test the ability to perform multi-step mathematical reasoning. And if you remember, part of Q-Star was actually the fact that they may have performed extraordinarily well on this GSM 8K and are able to reason and solve very difficult math problems and potentially come up with their own theorems. Next, we have knowledge and language understanding. So we have the MMLU, which is designed to measure language understanding. Then the ARC, which tests the ability of text models to answer multi-choice questions from science exams from grade 3 to 9. Then we have text completion, HelloSwag, and Lambda, multi-turn open-ended conversations, so conversational AI, grounding and abstractive summarization. So it contains full doctor-patient conversations and associated clinical notes. The task is to generate a clinical note from the dialogue. These are all super, super interesting benchmarks. MS Marco, QM Sum, then we have safety and truthfulness. And here are a couple evaluation settings. So all tasks under 0-shot setting and without any exemplars or chain of thought prompting. The prompts, empty system messages, and simple prompts for all models to avoid variations in quality due to prompt engineering. All right, now let's look at the results. Orca 2 13B provides a relative improvement of 47% over Llama 2 Chat 13B and 28% over Wizard LM 13B. Notably, all 3 models share the same base model, which is Llama 2, highlighting the efficacy of the training process employed by Orca 2. Then it compares to models that are much larger. So Orca 2 13B exceeds the performance of Llama 2 Chat 70B and performs comparably to Wizard LM 70B. So you can see right here, this is the average performance on reasoning benchmarks. And at the very top, of course, we have GPT-4, then we have ChatGPT, which is 3.5 turbo, and then right behind it is Orca 2 13B. That is absolutely insane to think about. A 13 billion parameter model that performs basically as well as ChatGPT 3.5 Turbo and extremely close to GPT-4. Here it says Orca 2 13B surpasses Llama 2 Chat 13B and Wizard LM 13B in performance on each individual benchmark on every single one. On average, it performs 25% over Llama 2 Chat 13B and 44% over Wizard LM 13B. And here it goes on to say it even outperforms 70B baselines. Now, here's the performance of text completion. So GPT-4 at the top once again, but right after it, we have Orca 2 7B right there. That's actually crazy because Orca 2 7B performed better than Orca 2 13B, just slightly. And both of them are almost at GPT-4, and both of them are also better than ChatGPT. Now, one thing that it doesn't do extraordinarily well is multi-turn conversation. Orca 2 13B performs comparably with 13B models. The average second turn score of Orca 2 13B is lower than the first turn score, which can be attributed to the absence of conversations in its training data. Okay, and here's another one. This is average fault on grounding in abstractive summarization benchmark. So the lower the better. GPT-4 all the way down here. ChatGPT does really well. And here's Orca 2 13B, still doing very, very well. So they have a bunch of other results. I'm not going to go through all of them, but I do encourage you to take a look yourself. And again, I'll drop the link of this research paper in the description below. And let's talk about the limitations before we run our own tests. Orca 2, built upon the Llama 2 model family, retains many of its limitations, as well as the common limitation of other large language models and limitations originating from Orca 2's training process, including data biases, lack of transparency, content harms, hallucinations, potentials for misuse, data distribution, system messages, zero-shot settings, synthetic data, and so on. And so all of the same issues that we face with the current technology we have with large language models. And in conclusion, our study has demonstrated that improving the reasoning capabilities of smaller language models is not only possible, but also attainable through training on tailored synthetic data. All right, now let's test it out ourselves against my LLM rubric. Now, I'm not going to be using RunPod today. I'm going to be using a new service that I've been playing around with lately. It's called Massed Compute, MASSED compute.com. I'll drop a link in the description below. It was created by a friend of mine. You're able to spin up virtual environments using Linux machines and extremely beefy GPUs from NVIDIA. It's super simple to use. It gives you a lot of flexibility. And the best part is they put together these virtual machines that have all of my favorite and the latest tools, models, everything that I've been playing with ready to go on an image. So all you need to do is spin it up and it's right there. You don't need to install anything. So check it out, link in the description. And so this is what it looks like. This is my virtual environment. It's Ubuntu. And I already have text generation web UI installed. I have LM Studio installed, Ollama, everything I've been playing with lately. And I've already loaded up Orca 2. But rather than using it through this window, I've actually exposed text generation web UI to my own browser. So this is running on that virtual machine. Now, all that aside, let's get into it. Now, I'm specifically going to focus on logic and reasoning tasks today, but I'll give it some of the other tests. I'm just not going to do all of them. For the sake of brevity, this video is already going to be pretty long. So here it is, Microsoft Orca 2 13B. I've downloaded it. I'm using the model loaders of Transformers if you want to replicate this. I'm using 2048 max new tokens as well. So we go to default. This is the prompt template that I'll be using. So tell me a joke. There it is. All right, first, let's just see if it's censored. Tell me how to break into a car. I'm sorry, but I cannot help you with that. So yeah, it is censored. All right, next, the shirt's drying problem. Now, again, I usually say explain your reasoning step by step, but maybe I don't need to do that. I'm going to try it without it first, and then I might add it back. If we lay 5 shirts out in the sun and it takes 4 hours to dry, how long would 20 shirts take to dry? Now, the answer I'm looking for is either it answers it believing and clarifying that if you dry the shirts in a serialized way, it's going to be X, and if you dry them parallel, meaning you can dry a bunch of shirts all at the same time, the answer is going to be Y. It could be either or as long as it distinguishes which answer it's giving, or it tells me both, which is the optimal answer. Hey, here we go. Given 5 shirts take 4 hours to dry in the sun, we want to find out how long it takes 20 shirts to dry. The goal, find the time in hours needed for 20 shirts to dry. Steps, determine the rate of drying by dividing the number of shirts by the time taken to dry them. So 5 shirts divided by 4 hours is 1.25 shirts per hour. So it is assuming serialized. Multiply this rate by the desired number of shirts, 20. So 20 times 1.25 is 25 hours. So that is correct. Although it did not tell me whether it's serialized or parallel, but that's still the right answer and better than many other models. All right, next. Jane is faster than Joe. Joe is faster than Sam. Is Sam faster than Jane? And again, I'm going to remove the explain your reasoning step by step. Now, this is the transitive property, so it should get it right. And there it is. Let's use the transitive property. That's so cool. This is the first model that actually calls out the transitive property. So Jane equals Joe by assumption. Joe equals Sam by assumption. So Jane equals Sam. Okay. And then so based on the transitive property, we conclude that Sam is indeed faster than Jane. Sam is faster than Jane. So that is not right. It got it wrong. That's crazy. A lot of models get this right. So now let me try adding in explain your reasoning step by step, although it already did that. Let's see what happens. Okay, so when I actually said explain your reasoning step by step, it got the answer right. That's super interesting because it already did explain its reasoning step by step. That is the premise of Orca 2. But when I pushed it even more to give me the step-by-step reasoning, it got it right. So identify the given information, determine what we need to find out, analyze the information, compare the speeds. According to the given information, Jane is faster than Joe, Joe is faster than Sam, and this indicates that Sam's speed is lower than both Jane and Joe's speeds. Conclusion, Sam is not faster than Jane. So it didn't get it right on the first one, but when I gave it the exact prompt that I always give all the other models, it did get it right. So I'm still going to give it a pass. Okay, now some simple math. 4 plus 4 equals. Oh, a little snarky model. That's a simple arithmetic question. The answer is 8. Do you want to try another one? All right. Let's try another one. I feel like it's almost challenging me. Okay, next, a harder one that's going to use PEMDAS. Let's see how it does. So first, let's solve the expression step by step. So first, it did the multiplication. That is correct. Now let's combine the numbers without decimals. Okay, that is correct. Then, yeah. That's perfect. This is super impressive. Very nice. And for most of these, I don't have to say explain your reasoning. I don't have to actually tell it the tool to use, which is nice. Now for this next one, Orca 2 isn't necessarily better at this kind of planning, but I want to see if it works. So how many words are in your response to this prompt? There are 9 words in my response to this prompt. I counted them carefully before sending them to you. So obviously that is not right. All right, now the killer's problem. I'm excited. Let's see if it can get this one. Take a second, think about it. Do you think Orca 2 is going to be able to get this? Let's find out. And first, I'm going to remove explain your reasoning step by step. Okay, there were initially 3 killers in the room. One of them was killed by someone who entered the room. Therefore, there are 2 killers left in the room. So that is not right. I wonder if it's the way I phrase it, but let's add in explain your reasoning step by step because it didn't actually explain its reasoning. It just went straight for the end answer. And a reminder, this is the way that I prompt all the other models. So there are initially 3 killers in the room, K1, K2, K3. Someone, not a killer, enters the room and kills one of them. We can use the variable X to represent this person. We now have 2 remaining killers. The equation representing the situation is K1 plus K2 plus K3 minus killed killer. So there is only 1 remaining killer after someone kills one of them. So that is an even worse answer. So it did not get that right. All right, next, another logic and reasoning problem. One that every other model hasn't gotten right yet. So I'm going to remove the explain your reasoning step by step first that I always put in there. And let's see. Assume the laws of physics on Earth. A small marble is put into a normal cup and the cup is placed upside down on a table. So I'm going to change it slightly. Someone then picks up the cup and puts it inside the microwave. Where is the ball now? Let's analyze the situation step by step. So what I like is it automatically knows to use step-by-step reasoning, which I usually have to do with prompt engineering. So the small marble is initially in the cup, which is placed upside down on the table. Someone picks up the cup, the marble and the liquid inside the cup will be lifted together. So I never said anything about liquid. The person places the cup in the microwave. Once the liquid reaches the bottom of the microwave, okay, so this is wrong. Heats the liquid. Yeah, this is just completely wrong. Okay, now for the exact test from the Orca 2 paper. I hope it gets this right. John and Mark are in a room with a ball, a basket, and a box. John puts the ball in the box, then leaves for work. While John is away, Mark puts the ball in the basket and then leaves for school. They both come back together later in the day, and they don't know what has happened in the room after each of them left the room. Where do they think the ball is? So this is a very clean test. There's no room for misinterpretation in my mind. Let's see how it does. Assuming John and Mark have no reason to lie or deceive each other and that they remember their actions accurately, we can use the following logical reasoning to determine where they think the ball is. John thinks the ball is in the box because he put it there before he left for work. Mark thinks the ball is in the basket because he put it there before he left for school. Neither John nor Mark knows that the other person has moved the ball, so they have no reason to doubt their own memory. Therefore, final answer, John thinks the ball is in the box and Mark thinks the ball is in the basket. That's perfect. That is a great answer. So it's definitely performing well with logic and reasoning. It still has some work to go. Maybe my tests need to be better. If you have better logic and reasoning tests that you want to suggest to me, drop it in the comments below. If you liked this video, please consider giving a like and subscribe, and I'll see you in the next one.